first have to ask you to adjust your minds to a new scale. Instead of statewide, this is a much smaller, 70 square mile watershed. Here's a picture that was taken in the last 2 months from the space station, and it's a great picture because, first off, it's home to Brigham Young University there on the other side of those mountains. This is Utah County in north central Utah. But more importantly is this reservoir right here. This is the Deer Creek Reservoir, and some of the water will go down into Utah Lake there in the top part of the picture, but it's also a major drinking water source in Utah for Utah and Salt Lake counties. We don't have that much water in the west. So again, you have to understand that we're really interested in protecting the water quality and what we do have. And this watershed here, outlined in white, is the Wallsburg watershed. So this watershed's been of interest to the state for decades now, because it contributes relatively small amounts of water to this reservoir, but a relatively high amount of phosphorus load. It's disproportionate. So let me introduce the watershed just briefly. And kind of the top third elevations, you have a lot of alpine ecosystems and forested areas. As you start to move down closer to the valley, you hit a scrub oak and sagebrush ecosystem. And then in the bottom of the watershed, which is only about 10% of the land cover, you have some very low intensity agricultural pastoral systems of hay and grass fields and alfalfa. It's very low intensity, no crops, in terms of like corn or soybean or anything like that. Maybe a couple hundred head of cattle that are grazed there, but yet phosphorus losses from this watershed have been of concern for years. So by way of hydrology, this watershed receives most of its annual precipitation as snow in the wintertime. Come spring, that begins to melt, and you start to see your first big flushes. But right around that time, some of that water a good deal of that water is diverted for agriculture, for irrigation. But starting about June all the way to September, sometimes October, there's very, very little rainfall up there. And so one of our questions was to try to understand better, not just what we're seeing in the water across the watershed, which we've been doing for the last 2 years with Dr. Hansen at BYU, but to understand more about the distribution of phosphorus in the soils. And so here's a map you can see in red of all the sites we've been to over the last 2 years. Sometimes we make soil sampling trips specifically. Other times we try to grab a couple sites when we go up there to do water sampling. So this is about 70 sites across the watershed, and it's not completely uniformly distributed. You can see as you get into some of the higher elevations, we're kind of limited to the tributaries and the canyons there. The terrain's pretty steep. But the question is, what are the phosphorus values there? So we've measured this doing a sodium bicarbonate extraction, or Olsen phosphorus. And at the low end, we have about 7 parts per million, and on the high end, about 82. But is an interpolation map like this really the best way to map soil phosphorus distributions across the watershed? I mean, this is just a simple interpolation. It doesn't take into account topography, hydrology, or vegetation cover, anything like that. So I was interested in seeing if we could do better, and that's primarily because of this figure here. So this is the distribution of soil phosphorus values. And you'll notice those agricultural fields tend to be some of the lowest P values in our watershed. I don't think that's very common for many other places, especially where there's dairy production or farming practices in place. But the areas of shrubland and woodlands tend to have much higher loosely absorbed phosphorus right there at the surface. And let me mention that this study that I'm presenting today, this is all about surface soil phosphorus in that top 5 centimeters. That's what we're most interested in, and whether or not that's going to erode or transport So this is not subsurface. This is just right at the top. All right, so introducing Maxent, sometimes displayed as Maxent. It's short for maximum entropy. Basically, it's a mathematical method, and I'm not going to really get into that because that's not the point of this talk. But Phillips and Dudek in the mid-2000s developed a software program around it. It's a really simple Java app that takes location data and environmental variables, and you can run some maximum entropy models off of that. And just do a quick Google search and you'll get there. All right, so why did I choose to use Maxent for modeling soil phosphorus distributions? Well, it's developed for presence-only data, and I'll get to that in a second. But it can also perform pretty well with limited data if you have a small sample size. But probably the biggest factor is I happen to know about it already. And why not try things you already know and see if you can apply it. See, the thing with Maxent, though, is it's an ecological tool. It's used widely in species distribution maps with plants and trees and things that don't tend to move like soil does. But hey, let's give it a shot. So going back to these soil sites that we've sampled, okay, so it has to do with presence-only data. So how do you say whether or not soil is present? Soil is present everywhere. So we had to set some kind of threshold to say what was absent and what was present. So it's kind of like looking for the right soil species, if you will. So we decided to set a threshold, and you might not think this is high or low or whatever, but it's split our data up in such a way that we were pleased enough to explore this method. And we ended up with about 38 present sites, in other words, sites at which the phosphorus, the sodium bicarbonate extractable phosphorus, was above 30 parts per million. And in terms of like Malic 3, for instance, we've done that analysis too. It's about 60 to 70 parts per million. So maybe not like that high, but it gave us somewhere to start. So right, Maxent takes these presence locations and it takes environmental variables. So I just tried to think of as many environmental variables as I could, starting with an elevation model and creating derivatives from the elevation model. Things that might predict soil transport in the watershed, erosion processes, just different terrain features, as well as some geologic layers, starting with the NRCS data and correcting it here and there, or not correcting it, but adjusting it here and there based on our own soil sampling data, and as well as a Utah Geologic Survey map of the parent material in the watershed. And why not? Let's just keep going. Let's just keep throwing some layers in. So we took some reflectance values. Maybe there's something we can learn from the vegetation at the surface, or the maybe there's something here in these layers. That's another thing with adding all these layers, is in some ways, I guess I'm not so concerned in this as to whether or not it directly relates to the distribution of soil phosphorus, or if it correlates with something else that we can go learn about later. But here's where it got kind of interesting. So this is one of the outputs that we received from Maxent. Maxent's really great in that way, that it automatically generates these probability distribution maps, as well as a suite of other data and plots. So let me zoom in a little bit so you can see it better. So this is a map that Maxent will spit back out. And this is not a map of where soil phosphorus is. It is a map of the probability of suitability of soil phosphorus being there. So that's kind of key. Understanding that a value of 1, which would show up as kind of a hot spot, like red, a deep red color. A value of 1 means that area is based on the parameters you put and based on your training and test sites. It is 100% suitable, or 100% probable that spot is suitable for soil phosphorus. So if you were to go sample it, do some ground truthing, you really shouldn't be surprised if your test did come back to match other sites with similar characteristics. Okay, so this model ended up, we ended up slimming it down to just 10 environmental inputs, with the top 5 predictors being solar radiation, terrain ruggedness. There was apparently information in the infrared band, and slope, and also parent material. This AUC number that the Maxent will generate was about 0.745, and all you really need to know about that is that a model with a value of 0.5 means that the model that Maxent came up with is really no better than a random guess. 0 being that everything was uniformly distributed, maximum entropy across the watershed, 0.5 being random, and then 1 being a model that's perfectly suited to your data. So not maybe the best model. A lot of ecological models are closer to like 0.9, but it's somewhere to start looking, right? If you're a watershed planner, you might be interested in some of these hotter spots in the watershed. If you're planning on new developments that might disturb those soils and facilitate erosion events. Like I said, it generates other useful information that you can start to look at which variables have the most information in them. You can go through and look variable by variable to see how the logistic output or the probability of presence changes as all other variables are held constant and this one changes. And that's important, right? Because you get a map, but does it even make sense? So you have to take time to go back and look at the data and see, okay, here's one of the parent material units, number 6 here. It's predicting really high. Let's go and study what that geologic unit was. Let's go figure out where it's located in the watershed and why that might be a predictor. Lastly, I included a neighboring watershed, which I was hoping Maxent would do better at predicting areas within this watershed that would be considered high, elevated soil phosphorus. But it turns out Maxent's very prone to sampling bias, and so as you can see, it's continued to limit most of its predictions within the watershed we sampled, and not so much in the neighboring watershed, despite having similar topography and hydrologic, climatic, sharing similar backgrounds. Okay, so hopefully I haven't lost anyone, but in our sampling, we saw that there were naturally occurring elevated concentrations of lucid bound phosphorus across the watershed. It's not so simple to say, well, because these streams are flowing through agricultural fields last, right before it goes into this reservoir, agriculture is probably where the phosphorus is coming from. Most of our high elevated P sites came from sagebrush systems and from these forested systems with much steeper slopes, much more prone to erosion. Okay, Maxent's limited. It's developed for plants, maybe not soil. But for me, that wasn't really the point. The point was to start to explore other methods that to allow a computer to do some of the hard mathematical work and figure out what's connecting these sites. Because if we can do better at interpolating and mapping areas within our watershed that have higher phosphorus, then maybe we can do better with watershed planning and making sure that we have our proper management practices in place. These are some of the people we worked with, especially the Utah Department of Environmental Quality, helped us with get started on this with introducing us to the watershed, and that's what I've got for you. Mm-hmm. Right. So we did measure pH on quite a few of the sites, and it was one of our soil layers. In there, we had pH and organic matter, texture, and things like that. That's another approach I guess we could take is let's just look at our sites, and we could do some multiple regression analysis on that. But I just wanted to explore Maxent's ability to assume nothing about the landscape, take these environmental layers and see if you can predict it.
Thanks very much.